Tonight, we follow the story of the sun, how it was born, how it burns, and how it will end. Welcome to the Orbit for Sleep channel. Let us follow the orbit of science and drift gently towards sleep. The sun is about 4.6 billion years old. Scientists learn this by studying the oldest meteorites in the solar system and by comparing the sun to other stars of similar mass. Our sun is not at the beginning of its life, but it is also far from its end. In terms of a human lifetime, the sun would be a middle-aged adult. This middle point is important because it shows us that the sun is stable and predictable for now. At the core of the sun, hydrogen atoms are fused together to form helium. This process is called nuclear fusion. To put it simply, nuclear fusion means that under extreme heat and pressure, tiny hydrogen atoms are pressed so tightly that they merge into helium. When this happens, an enormous amount of energy is released in the form of light and heat. This energy then travels outward from the sun's center, moving slowly through layers of plasma before it escapes into space. By the time it reaches Earth, it has traveled for millions of years inside the sun and about 8 minutes across the space between the sun and Earth. The sun is classified as a G-type main sequence star, often shortened to a yellow dwarf. The term may sound small, but it describes a star that is actually enormous. Its diameter is about 109 times that of Earth, and over 1 million Earths could fit inside it. Even though the sun is only an average-sized star compared to giants in the universe, for us it is unimaginably large and powerful. Right now, the sun is in a long-lasting phase called the main sequence. This phase lasts for billions of years. During this time, gravity pulls inward while the energy from fusion pushes outward. These two forces balance each other perfectly. If gravity were stronger, the sun would collapse. If fusion were stronger, the sun would expand too quickly. Instead, the two are in harmony, keeping the sun stable and shining consistently. From Earth, we experience this balance as a steady golden light that rises and sets each day. It feels calm and dependable, like a heartbeat that never fails. Imagine the sun as a great furnace, not roaring wildly, but burning with a controlled flame. For billions of years, this constant energy has lit the skies, warmed the oceans, and given power to the growth of plants and the survival of animals. Without this stable middle stage, life as we know it would not exist. The sun's current age and stage give us confidence about the future. It has enough hydrogen fuel to continue shining for about another 5 billion years. For humanity, this means the sun is not a fragile or unstable presence. It will continue to glow in the sky long after our civilizations change, rise, or fall. In the quiet vastness of space, the sun endures as a steady companion, ancient yet full of life, keeping watch over its planets and sustaining Earth with every beat of its nuclear heart. The sun, like every star, has a limited supply of fuel. Its energy comes from fusing hydrogen atoms into helium at its core, and the amount of hydrogen available is finite. Right now, about 70% of the sun's mass is hydrogen. This may sound like an endless supply, but in the scale of billions of years, even this fuel will eventually run out. Astronomers estimate that the sun has been burning steadily for 4.6 billion years, and it has enough hydrogen left to continue shining for about another 5 billion years. One stage of the sun is the longest and most stable part of its life. During this time, the sun produces a nearly constant amount of light and heat. The balance between gravity pulling inward and the outward pressure of a fusion keeps the sun stable. Because of this, the sun's brightness and temperature have not changed drastically over human history. To us, it feels eternal, but in cosmic terms, this balance has a clear expiration date. When we ask how long the sun will continue burning, we are really asking how much longer hydrogen fusion at its core can be sustained. Right now, the sun fuses around 600 million tons of hydrogen into helium every second. This number is difficult to imagine, but it shows how fast the sun is consuming its fuel. Even though the sun is massive, the scale of energy it produces means the fuel supply is not infinite. Still, because the sun is so large, it can maintain this process for billions more years. Over time, the amount of helium in the core increases while the amount of hydrogen decreases. This gradual change does not stop the sun immediately, but it does slowly alter the balance inside. As hydrogen runs low in the very center, the sun will eventually begin to fuse hydrogen in a surrounding shell, which will mark the end of its main sequence stage. That transition is still far in the future, but it is already written into the sun's destiny. To put this in perspective, humans have existed for only a few 100,000 years, while complex life on Earth has existed for just over 500 million years. The sun's lifespan is on a completely different scale. Even if all of human civilization were to vanish tomorrow, the sun would continue shining for billions of years more. In this way, the sun feels eternal to us, even though it is not immortal in cosmic terms. Imagine the sun as a great clock, ticking slowly through time. Each second, it consumes hydrogen and turns it into light that streams across space. From Earth, this appears as the daily rhythm of sunrise and sunset. But behind this rhythm is a process so vast that it will outlast entire species, civilizations, and perhaps even the memory of humanity itself. The sun's steady glow is like the breathing of the universe, calm and dependable, carrying on long after we are gone. Scientists have calculated that in about 1 billion years, the sun will grow hotter by about 10%. This may sound small, but it will be enough to disrupt Earth's climate and possibly make it difficult for life to survive. Still, the sun itself will remain in its stable burning stage for several billion years after that. Only when the hydrogen in the core is nearly gone will the true changes begin. So, how long will the sun continue burning? The answer is both comforting and humbling. Comforting, because we know the sun will not suddenly vanish in our lifetimes, or even in the lifetime of our species. Humbling, because we see that the sun's clock is always moving, and eventually its fuel will run out. The sun's steady flame will continue for billions of years yet, but in the grand story of the cosmos, even billions of years are only a chapter in the endless book of time. Every star has a turning point, a moment when it can no longer sustain the balance it has kept for most of its life. For the sun, this turning point will arrive when the hydrogen at its core is almost completely consumed. Right now, hydrogen fusion in the center is stable and powerful, but eventually the supply will shrink. When that happens, the very process that has fueled the sun for billions of years will begin to fail. This is the moment astronomers describe as the beginning of the sun's death. As hydrogen in the core runs out, the sun will no longer be able to fuse it in the center. The core will contract under the force of gravity, becoming hotter and denser. At the same time, hydrogen fusion will shift to a shell around the core, while the outer layers of the sun begin to expand. This expansion marks the transformation of the sun from a stable main sequence star into a red giant. To us, the sun will no longer look like the steady golden star we know today, but a much larger and redder star, swelling far beyond its current size. This process will not be sudden like an explosion. Instead, it will unfold over millions of years, an immense but gradual transformation. Imagine a steady flame that has burned evenly for ages, now flickering and swelling as its fuel changes. The sun's surface will grow cooler as it expands, giving it a reddish glow. Its brightness will increase, not because it is burning fuel more efficiently, but because its surface area will grow enormously. For Earth, this stage will be catastrophic. As the sun swells, it will radiate more heat and energy. Long before it reaches its maximum size, the Earth will become too hot to sustain life. Oceans will evaporate, atmospheres will strip away, and the surface will turn into a barren desert. By the time the sun fully enters its red giant phase, it may engulf the orbits of Mercury and Venus, and Earth itself may be swallowed or scorched beyond recognition. The moment the sun begins to die is not about its light suddenly vanishing. Instead, it is the point when the harmony of forces, gravity pulling in and fusion pushing out, begins to break down. The sun will no longer be a star in balance, but a star in transition. Its future path will be defined not by stability, but by change and decay. This stage is still billions of years away. Humanity and all current life on Earth will be long gone by then, whether by extinction or by migration to other worlds. Yet, in cosmic terms, the sun's decline is inevitable. Stars are not eternal flames, but living systems with lifespans, each moving from birth to maturity and finally to death. The idea that the sun will one day begin to die can feel unsettling, but it is also a reminder of the larger cycles of the universe. Just as seasons change on Earth, stars have seasons of their own. The sun's coming transformation is simply the next stage in its long story, a story written in the laws of physics and carried out on scales of time too vast for us to fully grasp. When the sun begins its decline, it will not vanish into darkness right away. It will enter a long and dramatic phase of expansion, a grand finale that reshapes the solar system. This moment, the start of its death, marks the end of the sun we know and the beginning of its final journey toward becoming something new. To imagine it is to look beyond the comfort of today's steady sunlight and see the truth, that even the star we depend on is bound to change, fade, and eventually pass away. The sun's journey from the main sequence to the red giant phase is one of the most dramatic transformations in the life of a star. For billions of years, the sun has maintained a delicate balance between two opposing forces, gravity pulling inward and nuclear fusion pushing outward. This balance defines the main sequence, a long and stable period where the sun produces light and heat at a nearly constant rate. But eventually, as hydrogen fuel in the core becomes scarce, the balance will be broken, and the sun will begin a slow but unstoppable metamorphosis into a red giant. The first step in this transition begins when the hydrogen in the sun's core is nearly exhausted. Without sufficient hydrogen, nuclear fusion in the center will slow down and eventually stop. Gravity will then take control, causing the core to contract and heat up. Temperatures inside the core will rise to extreme levels, and this increase will ignite hydrogen in a shell surrounding the core. This shell burning produces even more energy than before, pushing the outer layers of the sun outward. As a result, the sun will start to expand, and its diameter will grow hundreds of times larger than it is today. As the sun swells, its surface temperature will decrease. Although the core grows hotter, the expanded outer layer to spread the energy over a much larger area, making the surface cooler and giving the sun a reddish glow. This is why the sun will be called a red giant. Despite its cooler surface, the sun will become far more luminous overall, shining thousands of times brighter than it does now, simply because its surface will be so much larger. From Earth's perspective, this stage will be catastrophic. Long before the sun reaches its maximum size, the increase in brightness will disrupt Earth's climate. Oceans will boil away, the atmosphere will be stripped, and the surface will be scorched into a barren wasteland. Plants and animals will not survive, and the conditions will become unrecognizable compared to the blue and green world we know today. Whether Earth itself will be engulfed by the sun is uncertain. Some models suggest the sun's outer layers could swallow our planet, while others suggest Earth may barely escape, left as a charred and lifeless rock. This red giant phase is not unique to the sun. Stars similar in size follow the same path, moving from a long period of main sequence stability to a dramatic expansion. Larger stars undergo even more violent endings, sometimes collapsing in supernova explosions. But for stars like the sun, the red giant stage is the grand finale before a quieter end. This transformation is part of the natural cycle of stellar evolution, written into the laws of physics and confirmed by observations of countless stars in our galaxy. The process of expansion will last for hundreds of millions of years. From our human perspective, this timescale is impossible to truly imagine. Civilizations rise and fall in thousands of years, while species appear and disappear over millions of years. Yet, the sun's transformation will take place on a timescale so vast that even entire epochs of life on Earth would seem like brief flickers compared to the slow unfolding of the sun's fate. For astronomers, observing other stars at different stages of their lives provides a window into our sun's future. Red giant stars can be seen in the night sky today, their swollen shapes and deep red colors standing as reminders of what awaits our own star. These observations confirm that our sun's destiny is not unique. It is part of a universal cycle shared by countless stars throughout the cosmos. To picture the sun's transition, imagine a fire that has burned steadily for ages, suddenly fed by a new surge of fuel around its edges. The flame grows larger, spreading out in great arcs of light, while the center collapses inward, becoming hotter and denser. This balance of collapse and expansion gives the red giant its unique character, a star both dying and yet more brilliant than ever before. The journey from main sequence to red giant is not a failure or an accident. It is the natural path that stars of this size follow. In the vast theater of the universe, the sun's transformation is just another act in a story that spans billions of years. For Earth and humanity, the consequences will be profound. But for the cosmos, it is simply one more example of the endless cycles of birth, change, and death that shape the stars and galaxies. The end of the sun's life will not come with a single dramatic explosion, but with a gradual transformation into a much smaller and dimmer object called a white dwarf. After the sun has expanded into a red giant and exhausted most of its usable fuel, it will no longer be able to sustain nuclear fusion. At this point, the sun will begin to shed its outer layers into space, creating a vast and colorful shell of glowing gas known as a planetary nebula. This nebula will shine for tens of thousands of years, lit by the last remnants of energy escaping from the dying star, before eventually dispersing into the interstellar medium. What remains after this shedding is the sun's core, a dense and compact remnant. This core will no longer fuse elements, but it will still contain the collapsed matter of what was once the heart of the sun. It will be roughly the size of Earth, yet hold about half the mass of the sun. This extraordinary density means that a single teaspoon of white dwarf material would weigh several tons on Earth. Despite its small size, the white dwarf will glow faintly with residual heat, slowly cooling over billions of years. The white dwarf phase is not unique to the sun. It is the common fate of stars similar in size. Larger stars end their lives with violent supernovae, but stars like the sun die quietly, leaving behind these dense remnants. The white dwarf is a kind of stellar ember, the last trace of a once vibrant star, glowing dimly as it cools into darkness. From the perspective of the solar system, this transformation marks a profound ending. The sun's outer layers, now drifting into space, will form intricate patterns of light and gas that might resemble delicate cosmic clouds. Planets that survive the red giant stage will orbit a very different central object, not a blazing star, but a small dim core surrounded by the faint glow of leftover radiation. Earth itself is unlikely to survive intact, but even if it did, the world would orbit a star reduced to a cold and lifeless cinder. For billions of years after the sun becomes a white dwarf, it will continue to radiate residual heat, gradually cooling. Eventually, it may become what scientists call a black dwarf, an object so cold and dark that it no longer emits visible light. However, this stage is theoretical because the universe is not yet old enough for any black dwarfs to exist. The cooling process is so slow that even after the entire current age of the universe, white dwarfs remain faintly glowing. Imagining the sun as the white dwarf offers both a sense of sadness and awe. The mighty star that once bathed Earth in warmth and light will be reduced to a tiny glowing ember. Yet it is not the end of the story. It is the beginning of a new chapter. The material expelled in the planetary nebula will drift into space, carrying elements like carbon and oxygen that may one day form new stars, new planets, and perhaps even new life. In this way, the sun's death contributes to the renewal of the galaxy. The transformation into a white dwarf is the sun's quiet farewell. There will be no sudden disappearance, but a long, slow dimming. To us, it is a reminder that even stars have lifespans, and that their deaths are not only endings, but also opportunities for creation. The sun's final act will be both humble and essential, leaving behind the building blocks for future generations of stars and worlds, continuing the cosmic cycle that has shaped the universe since its beginning. At the heart of the sun lies the process that has powered it for billions of years, hydrogen fusion. This is the mechanism that allows the sun to shine, and it is the foundation of all life on Earth. Inside the sun's core, temperatures reach about 15 million degrees Celsius, and the pressure is unimaginably high. Under these extreme conditions, hydrogen atoms, the simplest and most abundant elements in the universe, are forced together. When they merge, they form helium and release a tremendous amount of energy in the process. To understand nuclear fusion in simple terms, imagine two tiny hydrogen atoms as lightweight building blocks. Normally, these blocks repel each other because they both carry positive electric charges. But in the sun's core, gravity provides the immense pressure needed to overcome this repulsion. When the hydrogen atoms are squeezed close enough, they fuse into a helium atom. This fusion converts a small fraction of the atom's mass directly into energy, following Einstein's famous equation, E equals mc squared. That energy is what creates the sun's light and heat. The scale of this process is staggering. Every second, the sun fuses about 600 million tons of hydrogen into helium. In doing so, it releases enough energy to power all life on Earth, as well as sustain the climates of all the planets in the solar system. Yet, because the sun is so massive, it can continue this process for billions of years before running low on fuel. Fusion is both incredibly powerful and surprisingly efficient, maintaining the sun's steady output without burning through its fuel too quickly. The energy created in the sun's core does not immediately escape into space. It begins a slow journey outward, bouncing between particles in the dense plasma that makes up the sun's interior. This journey can take hundreds of thousands or even millions of years before the energy finally reaches the surface. Once at the surface, the energy radiates outward as sunlight, traveling through space in about 8 minutes to reach Earth. The light that warms your face on a sunny day actually began its journey deep inside the sun long before humans even existed. Hydrogen fusion is not just source of light, it is also the origin of many of the elements that make up the universe. As stars like the sun fuse hydrogen into helium, they enrich the cosmos with heavier elements over time. While the sun is not massive enough to forge the heaviest elements, it is part of a grand process that ensures the universe is not just hydrogen gas, but a place filled with carbon, oxygen, and other building blocks of life. Imagine the sun's core as a vast, glowing furnace. The heat is so intense, the pressure so great, that matter itself transforms into light. This invisible process is constant and tireless, like a heartbeat at the center of our solar system. Without it, Earth would be a cold, dark rock, devoid of oceans, air, and life. With it, the sun becomes the giver of energy, the source of warmth, and the reason our planet is alive. Hydrogen fusion at the core is the defining feature of the sun's life as a main sequence star. It is what keeps the sun stable, what balances gravity, and what makes the sky glow every morning. In the grand story of the cosmos, it is a process both ordinary and extraordinary, common to stars across the galaxy, yet essential to the survival of every living thing on Earth. The sun's stability depends on a delicate balance between two powerful forces, gravity pulling inward and pressure pushing outward. Gravity is the force that draws all matter together. Because the sun contains more than 99% of the mass in the solar system, its gravity is immense, constantly trying to collapse the star into itself. Without a counteracting force, the sun would shrink rapidly under its own weight. The opposing force comes from pressure created by nuclear fusion at the sun's core. As hydrogen atoms fuse into helium, enormous amounts of energy are released in the form of heat and radiation. This energy pushes outward, resisting gravity's inward pull. The result is a stable equilibrium known as hydrostatic balance. For billions of years, this balance has kept the sun from collapsing or exploding, allowing it to shine steadily in the sky. To understand this balance more simply, imagine blowing up a balloon. Your breath pushes outward, while the elasticity of the balloon's surface pulls inward. If the two forces match, the balloon holds its shape. In the same way, the sun holds its shape because the inward pull of gravity is perfectly matched by the outward pressure from fusion energy. If one force were stronger than the other, the sun would quickly change. Stronger gravity would cause collapse, while stronger pressure would cause expansion. This balance is not static, but dynamic. At every moment, trillions of reactions take place in the sun's core, and gravity is constantly responding to changes in mass and density. Yet the overall effect is stability. The sun breathes, in a sense, but its breathing is so steady and long-lasting that to us it appears eternal and unchanging. The concept of hydrostatic balance is one of the most important in stellar physics. It explains why stars like the sun can remain stable for billions of years. It also explains why stars eventually change. As the sun consumes hydrogen, the balance slowly shifts. The core becomes denser, gravity pulls harder, and fusion must increase to keep up. This adjustment keeps the sun shining, but also leads it toward its eventual transformation into a red giant. From Earth, we see the result of this balance as the dependable sunrise each day. The light and warmth feel calm and permanent, but beneath this calmness lies an immense struggle of forces. Gravity works relentlessly to pull the sun inward, while fusion energy constantly resists. Neither side wins, and it is this stalemate that allows life on Earth to flourish. Imagine the sun as a vast scale, with gravity pressing down on one side and radiation pressure lifting on the other. The two forces remain in perfect harmony, creating the steady glow that lights our world. This equilibrium is not only the reason the sun shines, but also the reason we exist. Without it, the solar system would be dark, cold, and lifeless. The balance of gravity and pressure is a reminder of the fragile harmony that governs the universe. Stars are not eternal flames, but dynamic systems, their lives shaped by competing forces. For the sun, this balance has lasted for nearly 5 billion years and will continue for billions more. Eventually, the balance will break, and the sun will change, but for now it remains steady, a glowing reminder of the invisible forces that shape the cosmos. The sun is not only a source of light and heat, it also constantly releases a stream of charged particles called the solar wind. This wind flows outward in all directions, carrying with it electrons, protons, and other atomic particles from the sun's outer atmosphere, known as the corona. Though invisible to our eyes, the solar wind is a powerful force that shapes the environment of the entire solar system. The solar wind begins in the sun's hot corona, where temperatures reach millions of degrees. At such high temperatures, atoms are stripped of their electrons, forming plasma. This plasma escapes the sun's gravity because it is so energetic, flowing outward at speeds of hundreds of kilometers per second. As the wind spreads through space, it forms a vast bubble around the solar system called the heliosphere, which stretches far beyond the orbit of Pluto. The heliosphere acts as a protective shield, deflecting harmful cosmic radiation from deep space and helping to create a relatively safe environment for life on Earth. The solar wind has many visible and dramatic effects. When these charged particles collide with Earth's magnetic field, they are guided toward the poles, where they interact with the atmosphere. The result is the aurora borealis and aurora australis, the northern and southern lights. These shimmering curtains of green, red, and purple light are among the most beautiful natural displays on our planet, a direct result of the sun's invisible wind meeting Earth's protective magnetic shield. But the solar wind can also be disruptive. When the sun becomes more active, releasing bursts of energy called solar flares or coronal mass ejections, the solar wind intensifies. These events can disturb Earth's magnetic field, causing geomagnetic storms. Such storms can interfere with satellites, disrupt radio communication, and even affect power grids on Earth. Modern technology is highly sensitive to these disturbances, making the study of solar wind crucial for our daily lives. The solar wind also shapes the surfaces of other planets. Mars, for example, once had a thicker atmosphere and possibly liquid water on its surface. But because Mars lacks a strong magnetic field, the solar wind gradually stripped away much of its atmosphere. This left the planet cold and dry, with little protection from solar radiation. Earth's magnetic field, by contrast, serves as a shield that prevents this kind of erosion, helping to preserve our atmosphere and maintain the conditions necessary for life. Beyond planets, The solar wind influences comets as well. When a comet approaches the sun, its icy surface begins to vaporize, releasing gas and dust. The solar wind pushes these particles away from the comet, forming the characteristic glowing tails that always point away from the sun. Without the solar wind, comets would not display these spectacular features in the night sky. Imagine the solar wind as a constant breath from the sun, invisible but far-reaching. It sculpts the boundaries of the solar system, paints the skies with auroras, and sometimes reminds us of the sun's immense power through disruptions of our technology. Though gentle compared to the sun's light, the solar wind is a steady reminder that the sun is not a static ball of fire, but a dynamic star, actively influencing its surroundings every moment. For billions of years, the solar wind has carried particles into space, and it will continue to do so until the sun's very last days. In this way, the solar wind is both a sign of the sun's vitality and a force that connects our world to the larger environment of the cosmos. To better understand the sun's future, astronomers study the life cycles of other stars. Stars are born, live, and die according to their mass, and by comparing stars of different sizes, we can place the sun's journey in a broader cosmic context. While the sun is a medium-sized star, both smaller and larger stars follow very different paths, each offering insight into the variety of stellar evolution. Small stars, known as red dwarfs, are the most common type of star in the universe. They have far less mass than the sun, and because of this, they burn their fuel much more slowly. A red dwarf can remain in the main sequence for tens to hundreds of billions of years, far longer than the sun's estimated 10 billion years. These stars are incredibly stable and long-lived, but they are also faint, producing less light and heat. Planets orbiting red dwarfs may remain habitable for long periods, though such planets face challenges from strong stellar flares that these stars often release. Stars more massive than the sun live very different lives. A star with several times the sun's mass will burn through its hydrogen much faster. Its greater mass increases the pressure and temperature in its core, speeding up nuclear fusion. These stars shine brighter and hotter than the sun, but exhaust their fuel quickly, living only millions of years compared to the sun's billions. When their fuel runs out, they expand into red supergiants and eventually explode as supernovae. These violent events scatter heavy elements like iron, gold, and uranium into space, seeding future generations of stars and planets. Between these extremes lie stars similar to the sun medium. Mass stars spend billions of years in the main sequence, then expand into red giants before shedding their outer layers and leaving behind white dwarfs. This is the fate awaiting our sun. By studying stars currently in the red giant or white dwarf phase, astronomers can predict what the sun will look like billions of years from now. Comparing stars of different masses also reveals the role they play in shaping the universe. Small red dwarfs ensure long-term stability, providing gentle light over unimaginably long spans of time. Massive stars, though short-lived, enrich the galaxy with heavy elements, making planets and life possible. Stars like the sun sit in the middle, offering stability for billions of years and eventually contributing their material back to the cosmos. Observations from telescopes show us the full range of these life cycles. In star-forming regions, we see newborn stars emerging from clouds of gas and dust. In older parts of the galaxy, we find red giants swelling and glowing, and in other areas, white dwarfs cooling slowly in the darkness. Supernova remnants mark the violent deaths of massive stars, leaving behind neutron stars or black holes. Each of these stages provides a piece of the puzzle that helps us understand our sun's destiny. Imagine the universe as a vast symphony, with each star playing its part. The small red dwarfs hum quietly for eons, the massive stars burst like cymbals in explosive finales, and stars like the sun carry the melody steadily for billions of years before fading softly. By studying these varied rhythms, we learn that the sun's story is not unique, but part of a grand pattern that has repeated countless times across the galaxy. The life cycle of other stars shows us that death is not the end but a transformation. The matter expelled by dying stars becomes the raw material for new stars, planets, and even life. In this way, every star's journey contributes to the ongoing story of the cosmos. Our sun, too, will one day pass through this cycle, reminding us that it is part of a much larger and timeless process. While the sun will end its life quietly as a white dwarf, massive stars face a far more violent fate. The key difference lies in mass. A star much larger than the sun, perhaps 10 or more times its size, experiences much higher pressures and temperatures in its core. These conditions cause fusion to proceed at an accelerated pace, consuming fuel far more quickly. As a result, massive stars live fast and die young, surviving for only millions of years compared to the sun's billions. In a massive star, fusion does not stop with hydrogen and helium. Once hydrogen is exhausted in the core, the star begins fusing helium into carbon and oxygen. As temperatures rise further, it continues to fuse heavier elements, neon, magnesium, silicon, and eventually iron. Each new stage of fusion requires higher temperatures and pressures, and each one happens more quickly than the last. For example, while hydrogen burning may last millions of years, the final stage of iron buildup may last only days. The star's life accelerates toward a dramatic conclusion. Iron is the turning point. Unlike lighter elements, fusing iron does not release energy, it consumes it. When the star's core fills with iron, nuclear fusion can no longer sustain the outward pressure needed to counteract gravity. Without this support, gravity takes over and the core collapses catastrophically. The outer layers of the star then rebound against the collapsing core in a colossal explosion known as a supernova. A supernova is one of the most powerful events in the universe. In a single moment, it can outshine an entire galaxy, releasing more energy than the sun will emit in its entire 10 billion year lifetime. The explosion hurls the star's outer layers into space at tremendous speeds, scattering elements forged in the star's core. Gold, silver, uranium, and other heavy elements are born in these moments of destruction. Without supernovae, the universe would lack the diversity of elements needed for planets and life. The remnant left behind depends on the mass of the original star. If the core is small enough, it collapses into a neutron star, an incredibly dense object where protons and electrons are squeezed together into neutrons. A teaspoon of neutron star material would weigh billions of tons. If the star is even larger, the collapse continues until not even light can escape, forming a black hole. These objects warp space and time itself, representing the most extreme outcome of stellar death. The sun will never undergo such a fate because it is not massive enough to fuse elements beyond carbon and oxygen. Instead, it will gently shed its outer layers and leave behind a white dwarf. But by studying massive stars, astronomers can understand the role of these cosmic giants in shaping the universe. They live short but traumatic lives, and in their violent deaths, they enrich the cosmos with the elements that make life possible. From Earth, we occasionally glimpse the results of these stellar deaths. Supernovae have been observed throughout history, sometimes visible in the daytime sky. Ancient astronomers recorded these sudden bright stars with awe, not knowing they were witnessing the death of suns far larger than our own. Today, with telescopes, we can study supernova remnants, glowing clouds of gas that expand outward for thousands of years after the explosion. Imagine a massive star as a brilliant firework. It burns hotter and brighter than anything around it, dazzling the universe for a short time before ending in a spectacular explosion. The sun, by contrast, is like a steady candle, glowing softly for billions of years. Both play essential roles in the universe. The massive stars are the creators of heavy elements, while stars like the sun provide the stability for life to flourish. Their differences remind us that the cosmos thrives on diversity, with each type of star contributing to the great cycle of birth, death, and renewal. The fate of Earth is inseparably tied to the life cycle of the sun. As the sun evolves, its changes will gradually reshape the conditions of our planet, ultimately determining whether Earth can remain a home for life. Right now, the sun provides a steady flow of energy that keeps our climate stable and our ecosystems thriving. But over billions of years, that balance will not last. The sun's evolution will have consequences that reach every corner of our world. In the near future, on the scale of hundreds of millions of years, the sun will slowly grow brighter. Scientists estimate that in about 1 billion years, its energy output will increase by roughly 10%. While this may sound small, it will have enormous effects on Earth's climate. Global temperatures will rise, oceans will begin to evaporate, and the delicate balance that allows liquid water to exist on the surface will break down. The greenhouse effect will intensify as water vapor fills the atmosphere, trapping even more heat and pushing Earth into a runaway warming scenario. As this process continues, Earth will gradually transform. The seas will shrink and vanish, leaving behind salt flats and scorched landscapes. Plants, which rely on liquid water and moderate temperatures, will die off first, followed by animals that depend on them. Complex ecosystems will unravel until only simple heat-tolerant microorganisms remain. Over time, even these last traces of life will be wiped away by the relentless heat. By the time the sun fully enters its red giant stage, Earth will already be unrecognizable. The atmosphere will be stripped away by the intense solar wind, and the surface will become a barren desert of rock. If Earth is engulfed by the sun's expanding outer layers, it will be destroyed entirely. Even if it escapes direct consumption, it will be left as a lifeless husk, orbiting a star that no longer resembles the sun we know today. The impact of the sun's evolution is not only physical but also symbolic. Earth has existed in a narrow zone around the sun where conditions allow for liquid water and complex life. This zone is called the habitable zone, or the Goldilocks zone, because it is not too hot and not too cold. As the sun grows brighter, this zone will shift outward, leaving Earth behind. Planets farther from the sun, such as Mars, may briefly enter the habitable zone, but Earth will no longer be the cradle of life. Astronomers use Earth's future as a reminder of the impermanence of planetary environments. Just as Venus was once more Earth-like but became a greenhouse world, and Mars may have once had rivers and lakes, but is now frozen and barren, Earth's environment too will eventually collapse. The sun's changes make this outcome inevitable, no matter what humans or other species might do. Still, Earth's story under the sun is extraordinary. For billions of years, the sun has provided stable conditions that allowed life to emerge, diversify, and flourish. Every forest, every ocean, and every living creature owes its existence to the sun's steady energy. The changes that lie ahead remind us that this gift of stability is temporary. Earth has always been part of a larger cosmic cycle shaped by the life and death of stars. Imagine looking up at the sky in Earth's distant future. The sun would appear larger and more intense, its light harsher and more unforgiving. The blue skies we know would fade into a hazy glare. The oceans would be gone, replaced by vast deserts under an unforgiving heat. This vision is sobering, yet it is also a reminder of the power the sun holds over our world. The sun's evolution will ultimately strip Earth of its habitability, but in doing so, it will also pass on the elements that once formed our planet and our bodies into the wider universe. The Earth's destiny, like the sun's, is to become part of a cycle far larger than itself, a cycle of change that has governed the cosmos since the beginning of time. One of the most dramatic consequences of the sun's evolution will be the loss of Earth's oceans. Today, our seas cover more than 70% of the planet's surface, regulating climate, supporting ecosystems, and providing the foundation for all known life. But in the distant future, as the sun slowly grows brighter, this life-giving water will vanish. The disappearance of the oceans marks a turning point in Earth's history, transforming it from a living world into a barren desert. The process begins with a gradual increase in the sun's luminosity. As the sun continues to burn hydrogen in its core, its energy output rises by small amounts over millions of years. In about 1 billion years, this increase will be enough to raise Earth's average temperature significantly. The oceans will start to evaporate more quickly than rainfall can replenish them. Water vapor will accumulate in the atmosphere, amplifying the greenhouse effect and accelerating the warming cycle. As global temperatures climb, evaporation will intensify. The skies will become heavy with water vapor, thickening the atmosphere and trapping even more heat. This runaway greenhouse effect will resemble what happened on Venus, where surface temperatures today are hot enough to melt lead. On Earth, the oceans will slowly shrink, receding into smaller seas and isolated lakes before disappearing altogether. Salt flats and vast dry basins will replace the familiar blue expanses of water. Without oceans, the planet's climate system will collapse. The oceans act as heat reservoirs, absorbing warmth and distributing it around the globe. They also drive weather patterns from gentle rains to powerful storms. Without this regulation, Earth's surface will become subject to extreme heat by day and freezing cold by night. Rain will no longer fall. Rivers will dry up, and the hydrological cycle that has shaped Earth for billions of years will come to an end. The disappearance of the oceans also means the end of marine life. Fish, corals, plankton, and all other ocean-dwelling creatures will vanish as their habitat disappears. The collapse of the oceans will ripple outward, destroying coastal ecosystems and ending the cycle of water that sustains land-based life. Forests and grasslands will wither, and only the hardiest microorganisms might persist for a time. Eventually, even they will succumb to the rising heat. From space, Earth will no longer appear as the blue planet. Instead, it will look more like Mars or Venus, dry, desolate, and lifeless. The shimmering reflection of sunlight off the oceans, a feature that has inspired countless human observers, will be gone forever. Future civilizations elsewhere in the galaxy, looking at Earth from afar, would see not a water-rich cradle of life, but a barren rock orbiting a changing star. This transformation is not unique to Earth. Astronomers studying exoplanets know that the presence of liquid water is one of the most important markers of habitability. Planets too close to their stars often lose their oceans through runaway greenhouse effects, while those too far away remain frozen. Earth is fortunate to exist in a habitable zone for now, but as the sun grows hotter, our planet will inevitably shift out of this zone and lose the very feature that made it alive. Imagine standing on Earth in its distant future, watching the last seas shrink into shallow basins under a relentless sun. The air would shimmer with heat, and the horizon would be filled with dust instead of clouds. The sound of waves crashing on shores, a sound that has echoed for billions of years, would be silenced. What remains is a quiet, parched world, a ghost of the vibrant planet we once knew. The disappearance of the oceans marks not only the end of life, but also the end of Earth's identity as a water world. The sun, once the giver of life, will become the agent of its undoing, drying up the seas that nurtured the first living cells. Yet in this loss lies a cosmic truth. All planets, like the stars they orbit, are subject to the cycles of time. The oceans may vanish, but their memory will live on in the story of a planet that once thrived under the light of a middle-aged star. The sun's gradual evolution will not erase life on Earth all at once. Instead, it will unfold in a series of stages, each one removing more possibilities for survival until the planet is entirely barren. This timeline of extinction provides a sobering look at how fragile life is when faced with cosmic changes far beyond its control. The first stage will occur in the next few hundred million years. As the sun grows brighter, average global temperatures will rise. The increase may be small at first, but even slight changes can have profound effects on ecosystems. Plants and animals adapted to cooler climates will face stress, pushing species toward extinction. Polar regions will shrink, and tropical zones will expand. Some life will adapt, but the balance of Earth's biosphere will begin to unravel. In about 1 billion years, Earth's surface temperature will be high enough to trigger a runaway greenhouse effect. Oceans will start to evaporate more rapidly than they can be replenished. Water vapor will flood the atmosphere, trapping heat and accelerating the warming. Complex life, plants, animals, and ecosystems as we know them will no longer be able to survive. Forests will disappear, grasslands will wither, and the rich web of biodiversity that took billions of years to develop will collapse. Only microbial life, hidden deep underground or in protected niches, may persist. Over the following hundreds of millions of years, even microorganisms will struggle. As Earth loses its oceans, liquid water will become scarce or vanish entirely. Without water, the chemistry of life cannot continue. The atmosphere will thin as it is stripped away by the sun's intensified solar wind, leaving the surface exposed to harmful radiation. By this point, Earth will no longer be habitable for any form of life we recognize. By the time the sun enters its red giant phase, life will already be long gone. Earth will be a scorched rock, its surface barren and its skies empty. Whether the planet is eventually engulfed by the expanding sun or simply left as a lifeless husk makes little difference. Extinction will already be complete. The timeline ensures that long before the sun's final transformations, Earth will cease to be a living world. This progression may sound grim, but it highlights an important truth. Life on Earth exists within a narrow window of conditions. Too little heat, and the planet would freeze. Too much, and it will burn. For billions of years, Earth has been balanced in this habitable zone, a rare and precious gift in the cosmos. The timeline of extinction shows us how fleeting this gift truly is. Astronomers study this timeline not just to understand Earth's fate, but also to learn about other planets. By observing worlds around other stars, scientists can identify which ones may be habitable now, and which ones are already past their prime. Earth's future is a model for what happens when a planet leaves the habitable zone of its star. Imagine watching Earth through time-lapse across billions of years. First, green forests fade into deserts. Then, oceans shrink and vanish, leaving salt-crusted basins. Finally, the surface cracks under relentless heat, and the atmosphere thins to nothing. What remains is silence, a planet stripped of its living heritage. This vision underscores the fragile link between a star and its planets, a link that determines whether life can exist at all. The timeline of extinction is not meant to inspire despair, but perspective. It reminds us that while life on Earth will not last forever, its very existence is extraordinary. In the grand history of the universe, Earth's era of life is a shining chapter, a brief but brilliant moment under the light of a star that will one day fade. The sun's evolution is not only a scientific curiosity, but also a profound question for the future of human civilization. Our dependence on the sun is absolute. Every harvest, every breath of air, every drop of water is sustained by its steady light. Yet as the sun changes, humanity will eventually face challenges no technology can fully prevent. Understanding this impact allows us to imagine both the opportunities and limits of our long-term survival. In the near term, measured on the scale of thousands to millions of years, the sun will remain stable enough for human civilization to thrive. The gradual increase in brightness is so slow that it will not disrupt life for societies within the time frames we normally consider. Humanity's greatest challenges will likely come from our own actions, climate change, resource depletion, or conflict, rather than from the sun itself. But when we extend our gaze to the distant future, the picture changes dramatically. As the sun brightens over hundreds of millions of years, Earth will become increasingly hostile. Rising temperatures will stress ecosystems and food supplies. Even advanced technology may not be able to counteract the loss of oceans or the breakdown of the climate system. In such conditions, civilization as we know it cannot survive on Earth. Humanity would face a stark choice: adapt by moving elsewhere or accept extinction. This realization has inspired discussions of interplanetary migration. If human civilization endures long enough, it may expand outward, colonizing planets or moons farther from the sun. Mars, for example, could one day become habitable as the sun grows warmer and its habitable zone sifts outward. In the even more distant future, humanity might seek to settle on moons of the outer planets, such as Europa or Titan, which could warm enough to support liquid water. In this way, the sun's evolution may dictate the trajectory of humanity's expansion into the cosmos. Yet, even such strategies have limits. When the sun becomes a red giant, its expansion will make the inner solar system uninhabitable. Even Mars and the outer planets may not remain safe. To survive beyond that stage, humanity, or whatever descendants of humanity exist, would need to leave the solar system entirely. This would mean traveling to other stars, a task that requires technologies far beyond anything we possess today. The sun's future, therefore, challenges us not just scientifically but also philosophically. Can a species dependent on its star learn to outgrow it? For civilizations on Earth today, the sun's distant evolution may feel irrelevant. After all, billions of years is an almost unimaginable timescale compared to human history. But contemplating this future places our achievements and struggles into perspective. The rise and fall of empires, the creation of art and science, the triumphs and tragedies of human history, all of these occur within a brief window of stability granted by the sun. We live in a fortunate era, one where conditions are just right for civilization to flourish. Imagine a future historian, millions of years from now, studying the ruins of Earth. The planet might be dry and lifeless, but the traces of human civilization, fossilized cities, artifacts buried deep underground could remain. They would tell the story of a species that once thrived under a middle-aged star. Whether that story ends on Earth or continues among the stars depends on choices made across countless generations. The impact of the sun's evolution on human civilization is both a warning and invitation. It warns us that Earth is not a permanent home. The stability we enjoy is temporary. But it also invites us to dream of a future where humanity becomes a cosmic species, carrying the memory of Earth into new worlds. The sun's eventual death will reshape the solar system, but it does not have to end the story of human civilization. Instead, it can be the beginning of a new chapter, if we are able to reach for the stars. The ultimate question raised by the sun's evolution is whether humanity or its distant descendants can survive once Earth is no longer habitable. The sun's slow transformation guarantees that our planet will eventually become too hot for life. Oceans will evaporate, the atmosphere will vanish, and the surface will be scorched. If civilization endures long enough to face these challenges, survival will depend on escaping the boundaries of our home world and perhaps even leaving the solar system entirely. The first step in this journey would likely be colonization within the solar system itself. As the sun grows brighter, the habitable zone, the region where liquid water can exist, will shift outward. Mars may become more temperate, its frozen water melting to form rivers and seas. For a time, it could provide a new home for humanity. Farther up, moons like Europa, Enceladus, or Titan may warm enough to support environments suitable for life. Humanity might migrate step by step, following the shifting zone of habitability. But these solutions are temporary. Once the sun becomes a red giant, even Mars and the outer moons may no longer offer safety. The sun's expansion will flood the inner solar system with heat and radiation, and even worlds at great distances will be destabilized. To ensure long-term survival, humanity would need to find refuge around another star. This leap, interstellar travel, is one of the greatest challenges imaginable. The vast distances between stars make this task daunting. The nearest star system, Proxima Centauri, is over 4 light-years away. With current technologies, such a journey would take tens of thousands of years. To make interstellar migration possible, humanity would need revolutionary advancements, faster propulsion systems, long-term life support, and perhaps generation ships capable of sustaining communities for centuries. Another possibility is using advanced technologies that do not yet exist, such as harnessing nuclear fusion for propulsion, or even developing concepts like warp drives that bend space-time. Beyond technology, survival would also depend on cultural and biological resilience. A civilization capable of living among the stars must adapt to long voyages, new planetary environments, and the psychological challenges of leaving Earth behind. Over millennia, humanity itself may evolve biologically or technologically into forms better suited for cosmic life. In this sense, the question is not only whether humanity can survive beyond the sun, but also what humanity will become in the process. This vision may seem far removed from the present, but it offers perspective. Just as our ancestors once left Africa to spread across Earth, future descendants might leave Earth to spread across the galaxy. The forces that drove exploration, curiosity, and survival on Earth could one day carry us to other stars. The sun's eventual death is not just a threat, it is a motivation, pushing humanity to expand its horizons. Imagine a future where distant descendants of humanity look up at a different sky, orbiting a new star. They may remember Earth as a place of origin, a cradle of life under a sun that has long since faded. The oceans, forests, and skies of Earth will be gone, but their memory will live on through stories, knowledge, and perhaps even genetic traces carried to new worlds. Humanity's legacy would not end with the sun, but continue as part of the galaxy itself. Whether humanity can survive beyond the sun depends on choices made across countless generations. The timeline is generous. Billions of years remain before the sun's most destructive changes occur. But survival requires foresight, planning, and a willingness to dream on scales that dwarf human history. The question is not whether the sun will die, it will, but whether humanity can transform itself into a species that endures beyond the life of its star. If it succeeds, then the story of humanity will not be bound to Earth or even to the sun, but will become part of the larger story of the universe. The sun's eventual death is not unusual in the grand scheme of the universe. Stars are born, live, and die according to their size, and each type of star follows its own path. By comparing the sun's fate with the fates of other stars, we can see how ordinary and yet significant its ending will be. Small stars, such as red dwarfs, have a very different destiny. They are far smaller than the sun and burn their hydrogen fuel very slowly. Because of this, they can live for trillions of years, far longer than the current age of the universe. A red dwarf will never become a red giant like the sun. Instead, it will quietly continue fusing hydrogen for unimaginable spans of time until it eventually cools and fades. Compared to them, the sun's 10 billion year lifespan looks brief, a short spark in cosmic terms. On the other end of the scale, massive stars live fast and die young. A star many times larger than the sun burns through its fuel in just a few million years. These giants end their lives in spectacular supernova explosions, collapsing into neutron stars or black holes. Such deaths are violent and dramatic, scattering heavy elements across space. The sun, by contrast, is not large enough to explode. Its death will be quieter, marked by the gentle shedding of its outer layers into a planetary nebula and the formation of a white dwarf core. Stars similar in size to the sun share its fate. Across the galaxy, astronomers see countless red giants, planetary nebulae, and white dwarfs. These observations confirm that the sun's future is not unique, but part of a well-understood pattern of stellar evolution. Its death may not be as dramatic as a supernova, but it is no less important. In fact, stars like the sun are crucial to the enrichment of the galaxy. The material they release in their final stages, carbon, nitrogen, and oxygen, are the building blocks of life. When compared to other stars, the sun's death falls into the middle ground. It is neither the endless endurance of a red dwarf nor the explosive finale of a massive star. Instead, it is a balanced story, long stability, followed by a graceful decline. This balance has made the sun ideal for nurturing life on Earth. It has provided billions of years of stable energy and will continue to do so for billions more before fading away. Imagine standing in a field of stars, each one living out its own story. Some are faint and eternal, others bright and short-lived, and the sun sits somewhere in between. Its ending may not light up the galaxy like a supernova, but it will leave behind a legacy just as profound. Every breath we take, every tree, every ocean wave is tied to the sun's steady energy. Its eventual transformation into a white dwarf is not the end of that story, but the continuation of a cycle shared by stars everywhere. In comparing the sun's death with that of other stars, we see a larger truth. The universe thrives on variety. Each star's death plays a role in shaping the cosmos. Red dwarfs provide stability, massive stars forge heavy elements, and medium stars like the Sun create the conditions for life. Together, they weave the fabric of galaxies. The Sun's death, quiet though it may be, is one thread in this immense and interconnected cosmic tapestry. The death of the Sun will reshape the solar system in ways that are almost unimaginable. For billions of years, the Sun's steady light has been the center of gravity, literally and figuratively, holding the planets in orbit and providing the energy for life on Earth. When the Sun reaches the end of its life and becomes a white dwarf, the solar system will be forever changed. As the Sun expands into a red giant, it will shed much of its mass into space. Gravity depends on mass, so when the Sun loses a large portion of its material, its pull on the planets will weaken. The orbits of the surviving planets will expand, drifting farther away from the dying star. Some planets and smaller bodies may even escape the solar system entirely, set free by the reduced gravity. The familiar structure of the solar system will become looser and less orderly than it is today. The innermost planets will face the most dramatic fates. Mercury and Venus will almost certainly be engulfed by the Sun's outer layers during its red giant phase. Earth may meet the same end, swallowed whole, or it may just barely escape, left as a scorched, lifeless rock orbiting a dim star. Mars could survive, but it too will be stripped of its atmosphere and any chance for life. The once vibrant inner solar system will be reduced to silence and ruin. The outer planets of Jupiter, Saturn, Uranus, and Neptune will likely survive, but their environments will be transformed. Without the Sun's stable heat and light, their atmospheres and moons will change. Some moons briefly warm during the Sun's red giant phase will cool again once the Sun contracts into a white dwarf. Frozen worlds like Europa or Enceladus will return to darkness, their icy shells hardening once more. The spectacular rings of Saturn may drift apart as gravitational balances shift. Comets and asteroids in the distant Kuiper belt and Oort cloud will wander in altered orbits, their paths disturbed by the Sun's reduced mass. At the heart of this changed system will be the white dwarf Sun, a small dim ember of what was once a powerful star. About the size of Earth but far denser, the white dwarf will glow faintly with leftover heat. It will no longer produce new energy through fusion. Instead, it will slowly cool over billions of years, becoming dimmer and dimmer until it is invisible to the naked eye. Around it will orbit the scattered remains of a once bright system, silent and frozen. To an observer from afar, the solar system will appear very different. There will be no brilliant yellow star shining at its center, only a faint point of light. The inner planets will be gone or lifeless, while the outer giants drift farther from the Sun's weakening pull. The belts of asteroids and comets will still exist, but their orbits will be unstable and stretched. The solar system, once vibrant with life and energy, will become a graveyard of worlds. And yet, even in this quiet aftermath, there is continuity. The material expelled from the Sun as it dies will not vanish. It will mix into the galaxy, enriching the interstellar medium with carbon, oxygen, and other elements. This material may one day form new stars, planets, and even the seeds of new life. In this way, the solar system's transformation is not an ending, but part of the endless cycle of renewal in the cosmos. Imagine standing on a surviving moon in the far future, looking up at the sky. The Sun would no longer dominate as a blazing disk, but as a dim white spark against the blackness of space. The planets would circle more distantly, and the solar system would feel emptier, quieter. What was once our warm and lively home will be reduced to a cold, fragile remnant. Still, the story of the solar system will not be over. It will live on, scattered among the stars. As the Sun moves toward its inevitable death, the question arises: where could humanity, or any descendants of humanity, find a new home? The Sun will no longer be able to sustain Earth, and if our species is to survive, it must look beyond its birthplace. This search for new suns and new worlds is both a scientific challenge and a philosophical journey, pushing us to consider our place in the universe. The first step in this search is identifying stars that could serve as new homes. Astronomers have already cataloged thousands of exoplanets orbiting distant stars. Some of these planets lie in the so-called habitable zone, where temperatures allow liquid water to exist. Stars similar to the Sun, stable and long-lived, are prime candidates for hosting such planets. G-type stars like our Sun or slightly smaller K-type stars may provide billions of years of stability, enough time for civilizations to take root and flourish. But scientists also look to red dwarfs, the most common stars in the galaxy. Though small and dim, red dwarfs can live for trillions of years, far longer than the Sun. Their longevity offers a kind of cosmic security, but they also pose challenges. Red dwarfs often produce powerful stellar flares that can strip atmospheres from planets. Any search for a new home must weigh the benefits of stability against the risks of violent stellar activity. The discovery of exoplanets in recent decades has transformed our understanding of what is possible. Worlds like Proxima b, orbiting the nearest star to our Sun, lie within their star's habitable zone. Others, like those in the TRAPPIST-1 system, present entire families of Earth-sized planets orbiting a single star. These discoveries suggest that habitable worlds may be common, waiting to be found. The search for new suns is not only scientific, it is also a search for potential futures for humanity. Finding a suitable planet is only part of the challenge. The distances between stars are immense. Even the closest stars are light years away, requiring technology far beyond what we currently possess. Reaching them would demand propulsion systems that can sustain journeys lasting thousands of years, or breakthroughs that allow faster travel through space. This makes the search for new suns not only about astronomy, but also about engineering, survival, and the resilience of civilizations. Philosophically, the search raises profound questions. If humanity settles around another star, would it still feel connected to Earth and the Sun? When most civilizations see themselves as exiles from a dying system or as pioneers of a cosmic journey, each new sun could become the center of a new culture, a new history, and perhaps even a new version of what it means to be human. The search is not just about survival, but about transformation. Imagine a far future where humanity lives under a different sky. Instead of the familiar yellow sun, another star, perhaps dimmer, perhaps redder, dominates today. Oceans and forests thrive under its light, and generations grow up never having seen the original sun. Yet in their stories, songs, and science, the memory of Earth and its star remains. The search for new suns is not simply about leaving the old one behind, but carrying its legacy forward. The death of the sun ensures that one day our solar system will no longer be habitable, but it also opens the possibility of new beginnings. By searching for new suns and new homes, humanity embraces its role as a cosmic species, not bound forever to one planet or one star. The journey will be long and uncertain, but it reflects the deepest instincts of life: to endure, to adapt, and to seek light even in the face of darkness. The sun's story is only one chapter in the vast book of cosmic history. To understand its meaning, we must see it in the context of all stars and their role in the universe's future. Stars are the engines of creation, the furnaces where matter is transformed into light and heavy elements. They are not eternal, but for as long as they exist, they shape the destiny of galaxies and the possibility of life. In the present universe, stars provide structure and energy. Their gravity binds galaxies, while their radiation drives the climates of planets. Fusion in their cores produces the elements that form planets, oceans, and living beings. Every atom of carbon in our bodies, every molecule of oxygen we breathe, was once forged in a star. In this way, stars are not just distant points of light, but ancestors of life itself. Looking to the long future, stars will continue to govern the cosmos. For trillions of years, red dwarf stars will burn quietly, long after the sun and similar stars have faded. These faint but enduring stars will serve as beacons in an increasingly dark universe, providing warmth and stability for possible life far into the future. Civilizations that exist in those distant times may gather around red dwarfs as the last havens of light. But even red dwarfs cannot last forever. Over unimaginable timescales, all stars will eventually exhaust their fuel. As they die, they will leave behind remnants, white dwarfs, neutron stars, and black holes. The universe will slowly shift from a place filled with bright stars to one filled with faint, cooling embers. Galaxies will dim as fewer new stars are born, and the cosmos will become quieter. In the very distant future, billions upon billions of years ahead, even stellar remnants will cool and fade. White dwarfs will become black dwarfs, invisible in the darkness. Neutron stars will gradually lose their energy, and black holes will dominate. Yet even these giants will not last forever. Through processes like Hawking radiation, black holes themselves may eventually evaporate, leaving behind a universe with no sources of light at all. This long view is sometimes called the heat death of the universe, a state where energy is evenly spread and no structures remain. In that future, stars, galaxies, and even atoms may no longer exist in familiar forms. The role of stars, then, is temporary but essential. They are the actors of the universe's middle age, shaping worlds and life before giving way to silence. For humanity, reflecting on this timeline is humbling. We live in a privileged era, when stars like the sun still shine and galaxies still form. The night sky filled with stars is not a permanent feature of the cosmos, but a fleeting moment in its long evolution. The brilliance we see above us is part of a temporary but glorious phase of the universe's life. Imagine the universe billions of years from now. The skies would be darker, with fewer stars, until eventually only faint glimmers remain. Civilizations alive in that time would know a quieter, lonelier cosmos, where the memory of bright suns is history. For us today, the stars are plentiful and vibrant, reminders of the creative power of the universe. The role of stars in the long future of the universe is both cosmic and personal. They give us the elements of life, the warmth of daylight, and the beauty of the night sky. Their eventual fading reminds us that everything, even the brightest light, is temporary. Yet in their brilliance, stars leave behind the seeds of what comes next, ensuring that the cycle of creation continues even in the face of eventual darkness. The eventual death of the sun invites us to think beyond science and into the realm of philosophy. Stars, like living beings, are born, change, and die. Their mortality, written into the laws of physics, mirrors our own. Just as humans must face the reality of finite lives, so too must we accept that even the star that sustains us will one day fade away. This realization is both unsettling and profound, forcing us to ask, what does it mean to exist in a universe where nothing lasts forever? Cosmic mortality reminds us that impermanence is not a failure, but a natural truth. The sun's death is not a catastrophe in universal terms, but a transformation. Its elements will return to the galaxy, contributing to the birth of new stars and planets. In this way, endings are also beginnings. The sun's mortality ensures continuity, because only through the death of stars do new worlds and new possibilities emerge. This cycle of death and renewal is the heartbeat of the cosmos. For humanity, the knowledge of the sun's mortality is both a challenge and an inspiration. On one hand, it shows the fragility of our existence. Life on Earth depends on conditions that will inevitably vanish. Our oceans, our atmosphere, even the ground beneath us are temporary gifts sustained by a star with a finite lifespan. On the other hand, this awareness deepens our appreciation of the present. Knowing that the sun will not shine forever makes its light more precious. Every sunrise becomes a reminder of the fleeting but extraordinary chance to be alive in this moment of cosmic history. Throughout human culture, the sun has been a symbol of constancy and power. Ancient civilizations worshipped it as a god, seeing its daily rising as proof of divine order. Modern science has revealed its true nature, not eternal, but finite, a star among countless others. Yet, rather than diminishing its significance, this knowledge makes the sun even more meaningful. It is not a divine miracle, but a natural one, a ball of plasma sustained by fusion, fragile yet capable of sustaining life for billions of years. Reflecting on cosmic mortality also reshapes how we view ourselves. If even stars die, then our lives, brief as they are, fit into the same universal pattern. Mortality unites us with the cosmos. The death of the sun, though billions of years away, connects us to the larger rhythm of existence: birth, growth, decline, and transformation. Seen in this light, our impermanence does not lessen our value, but situates us within something far greater. Imagine watching the night sky in the distant future, when stars are fewer and the universe grows darker. To the beings alive then, light itself will be a rare treasure. They may look back at our era as a time of abundance, when the heavens blazed with stars. Our present then is extraordinary, not just for us, but for the history of the cosmos. Recognizing this fills our short lives with meaning, even as we acknowledge their brevity. Cosmic mortality teaches us humility. The sun, so central to our existence, is but one star among billions that destined to fade like all the others. Yet it also teaches us gratitude. We are here now, alive under its light. In its brilliance, we find warmth, energy, and the chance to contemplate the universe itself. The fact that this light is temporary does not diminish its value, it enhances it. In the end, reflecting on the sun's death is not about despair but perspective. The universe is vast and impermanent, and we are part of its story. The mortality of stars mirrors our own, reminding us to cherish the fleeting brilliance of existence. Just as the sun will give back its elements to the galaxy, we too contribute to the cycle of life, knowledge, and meaning. In the face of cosmic mortality, we find both our limits and our place in the endless rhythm of the universe.